The second solution we want to talk about is iterative least squares solution. So we have the error function now, which is the sum of squared errors. We can write it like this: W transpose ith x minus ith y squared. If it is the j, the function that we want to reduce to equate to 0, then we want to scale it. Scaling a number to half doesn't hurt anybody. We just want to do it for convenience of taking derivatives. In theory, when we want to do optimization iteratively, we do it like this. For every w, if there is just one variable, there will be two w's, intercept and slope. If there are n variables, there will be n plus 1 w's. So for every w, when we want to update it, we will start by randomly initializing w's, but random initialization will give us an error. That error will help us update the w's. So on time t plus 1, we will change the weight, jth weight of the linear solution as much as the partial derivative of the error function with respect to jth weight. In short, we want to find the component of the error caused by this particular w. I'm going to call w to represent the coefficients of the model, the intercept and the parameters that we want to use to create a linear solution. So each coefficient will contribute something to the error. We want to extract that component and update that particular w as much as it caused the error, so that one day, we hope, when we repeat this many times, we will find the w set of w's, if there are many, that produced the least error. So how do we update? How do we calculate this partial derivative? We just take this half inside and take the derivative of this error function, and the 2 gets cancelled. The derivative of the error with respect to jth w will give us xi of jth. So this is the amount that we are going to calculate to update jth parameter, jth coefficient, or jth w. Notice we are updating it as much as the error multiplied by the jth x value of ith. This works because we don't have to do inverse of a large matrix. So iteratively, it will take some time, but one day, after a few iterations, in most cases, we are bound to find the global optimum. Eta, or step size, how much, we never know. Depending on the problem, we usually, heuristically, we start with large size, like 0.1 maybe. Every time we find wj is caused out of 10, 50% is caused by wj, we slash it by 10 and update the wj. And as we progress, we try to reduce the step size so that when we go near the global minima, we don't jump over it to the other side, and we slow down our update. And from 0.1, then 0.05, then 0.01, then 0.005, then 0.00. As we progress through our training, we reduce eta, step size. But since it's a heuristic, we let's get to the basics. Get the basics clear first, then we will see how we will discuss how eta will be helpful in finding the iterative least square solution quicker and stabler. So there are some bells and whistles. This is one of them that let us get some insight into the learning process. Step size is one of them, and then the error rate. How much is it reducing? If it is reducing by large strides in the beginning, and then there's a plateau for 200 iterations, it's just reducing and then coming back and then reducing, and that means we are stuck somewhere. So we need to look at those things to make the training more efficient. By training, what I mean is that we take the sample. Every sample goes through the this function is very simple. It's a linear function. We multiply w's with the sample x's and sum them, compare with the label, compare with the ground truth, compare with the y. Difference is error. If that we want to take that error and adjust our weights. Example by example, we keep doing that, keep doing that. And the formula we use to adjust our weight is this one. As much as the error over all data points multiplied by the feature value. Again, I want to set our common page here. So in here, in this X matrix, we have M features, M columns, N rows, N examples. We multiply mth feature to with the error to update mth weight. Does it make sense? We multiply jth feature value in ith example with the error caused by particular jth weight to update jth weight. You won't get this description in the textbook. It is easier to understand it like that. That's why I put it in these words, so that when you look at equations, you don't freak out. If you have easier way to express what's going on. So here, what's going on? We are multiplying. In the ith example, we get some error. The error is this one. And that error is multiplied by the jth feature because we want to update jth weight vector. So jth feature value gets multiplied by the error, and we add all the errors for the whole data set to calculate the responsibility of jth vector. And we update that as long as this update goes near zero. So there will be a point when we go to global minima, the updates will be very, very, very minimal. So we stop. When we see that the update size is so small, less than epsilon 0.0000 something, that is also a heuristic value, 0.0005. Less than that update size, we say we converged. We found the global minima, or we are almost there. So no need to waste more time. Let's get satisfied with this much error. If we spend one more day here, we will get maybe 2 points more, but there is no need. So let's go out. So we say the algorithm converged. So till now, we looked at analytic way of representing the solution to regression in the iterative least squares way.